In gases, we have to use a particular set of units in gases. Now, the first unit that we have is going to be pressure. And its symbol is P. P for pressure, uppercase P. And it has units, either 1 atmosphere, which equals 760 torr, or 760 millimeters mercury. Okay, those are the units. Now, what exactly is pressure? Pressure is the force on the container walls. All right, so pressure is a force on the container walls, and these are our units that we have. We have 1 atmosphere, 760 torr, and 760 millimeters mercury. These are all equal to each other. Okay, now right now, in this room, or while you're watching this video, the pressure is about 1 atmosphere, and it is about 760 millimeters mercury. That's the pressure at about sea level, which Winterville, Greenville is. We're just about at sea level. Okay, and so these are equalities. Now, you know, anytime we have an equality, we can write it as a conversion factor. We can write it as a conversion factor. So I can say this is 1 atmosphere for every 760 millimeters mercury. I can also say that we have 1 atmosphere for every 760 torr, and I can use these in conversion factors. Like, for instance, if I wanted to go from atmospheres to millimeters mercury, well, I would say something like, well, if I've got 1.58 atmospheres and I want to go to millimeters mercury, well, the magic number is 760. But remember, we're going to draw a line, and we've got to match up units. So units, we've always got to cancel units. And so atmospheres has got to cancel. I'm looking for millimeters mercury, then that would be 760 millimeters mercury for every 1 atmosphere. And by the way, since these are defined, they don't count for significant figures. So we put this on my calculator. Let's see what we get here. 1.58 times 760, and I get 1,200 torr, or 1,200 millimeters mercury. 1,200 millimeters mercury, which would be the same in torr. Millimeters mercury and torr are the same number that you're going to use. Now, this would be 3 significant figures. This doesn't count for 3 significant figures. This worked out to be 2, written like it is. So we probably should go ahead and put this in scientific notation. 1, 2, 3 millimeters mercury. Or we could just write off to the side that this is supposed to be 3 SF off to the side. But at the end of the day, what are we doing here with these? We're using them as conversion factors that go back and forth between the different kinds of pressure units. And so the next kind of unit that we have to use is the volume. And its abbreviation is V. V for volume. And volume is the space occupied. If you remember back in chapter 2 when we talked about units, volume is the space occupied. Mass was the amount of matter that you had. So right now we have the space occupied for volume. Now, the units for gases is usually it's liters or milliliters is what we're going to use for our units for gases. Now, the relationship between milliliters and liters is that there's 1,000 milliliters for every liter. Because a milli means 1,000th, and so we can say that there is 1,000 milliliters for every liter. And so we can also use this as a conversion factor to go in between milliliters and liters to milliliters. Let's say we had 84.6 milliliters, and I want to put that in liters. Well, I'm going to use this as my conversion factor. Here it goes. And, well, same rules apply whenever we use conversion factors. We've got to make sure units match up. Units match up, so what goes down here? We're going to need milliliters down here. And so we say a liter is 1,000 milliliters. Once again, this conversion factor right here doesn't count for significant figures because this is a defined quantity. It's 1,000 milliliters to a liter. It's defined, doesn't count for significant figures. And so when we put this in our calculator, we would actually say 84.6 divided by 1,000, and I get 0.0846 liters. 0.0846 liters. So we've gone from milliliters to liters. We can do the same thing. We'll have opportunities to go back and forth between milliliters and liters. Which one you happen to use depends on the problem. If your problem, some problems you can use either milliliters or liters. Some kinds of gas law problems which we're going to use, you have to use liters. More on that later. But generally speaking, you sometimes have a choice and sometimes you don't as to which units you use for volume. Next up, we have temperature. Now, in the previous two units when we did pressure and volume, we had some choices. We had some choices in what the units could be. When we had pressure, we could use atmospheres, millimeters mercury, torr, we could do that. When we had volume, we had some choices there. We potentially can use either milliliters or liters, depending on the problem. But when we get to temperature, you have no choice as to what units you can use. You must use Kelvin. Notice that I double underlined and I put exclamation points on there. It is absolutely critical that you use Kelvin when you're doing calculations using gas laws. The reason why we have to use Kelvin is because Kelvin has no negative numbers. And you may say to yourself, well, why does that matter? Well, we're going to do calculations where we're going to have something like this, like a pressure and a temperature, P1, T1, P2, V2, P2, T1. We might have a calculation that looks like this, and if I have a negative temperature anywhere in here, and I got a positive pressure over here, well, guess what's going to happen? When we're looking for the new pressure, we're going to get a negative pressure. We're going to get a negative pressure. There's no such thing as a negative pressure. If you do calculations in degrees Celsius, you can have negative numbers for degrees Celsius. So you can end up with negative volumes, which doesn't make any sense because once you shrink something down and it reaches zero, there's nothing less than being zero. All right? So the volume can't be less than zero. It's got to be some sort of positive number. The pressure's same way. You can't have a negative pressure. You can go all the way down to zero and that's it. So Kelvin avoids this problem. Kelvin avoids this problem right here. Since it has no negative numbers, you can't help but get the right number to making it positive. Now, since we must use Kelvin, well, most of the time, 99% of the time when you have a problem, the problem's going to be in degrees Celsius. So what are you going to do? It turns out that Kelvin is equal to the degrees Celsius plus 273. That's what it is. So if you have degrees Celsius, the very first thing that you have to do for any gas law problem is you're going to have to put it in Kelvin. After you do the problem, if one of your answers is in Kelvin, you're going to want to put it back into degrees Celsius. So you would say degrees Celsius is the Kelvin temperature minus 273. So for all gas law problems, you have to be in Kelvin. You almost always will end up going from degrees Celsius to Kelvin and from Kelvin back to degrees Celsius. It's almost always going to happen. All right. Now, one last fact here. Let me go ahead and erase this right here. One additional fact is that the kinetic energy of the gas of the gas molecules is directly proportional to the Kelvin temperature. Now, what does this mean? When I say, the kinetic energy of gas molecules is directly proportional to Kelvin temperature, well, think about this. Kelvin, or any temperature scale, is a measure of kinetic energy. You may recall some time ago, we're talking about, SI units in Chapter 2, and, what are we truly measuring? We measure temperature. If we have a solid, it's not really sitting there just all stuck there. It's actually got a little bit of wiggling going on. Even liquids, they'll wiggle. And so the harder the wiggling, the higher the temperature. The less the wiggling, the lower the temperature. Well, gas is the same way, except, they're all very far apart, with KMT, kinetic molecular theory. But the more heat you have, the more energy you have, the faster the molecules are going to be moving. Well, what's kinetic energy? It's the energy of motion. So the faster they're going, the hotter they are, the higher the kinetic energy of the individual gas molecule. So what it comes down to is to be directly proportional means that if you double the Kelvin temperature, you're going to double the kinetic energy of the gas molecules. And if you take the temperature in half, well, you're going to take the kinetic energy of all those individual gas molecules, and you're going to cut that in half as well. Now, the last unit that we're going to use for gas law calculations, and all gas law problems are going to use just these units, the last one is the amount. Now, the amount is actually the number of moles. You remember moles. Moles you get from, it's a counted quantity, all right? It's the number of moles. A mole will be in 6.02 times 10 to the 23rd of anything. And the symbol that we're going to use is different from the rest of them. Like P was pressure, V was volume, and T was temperature. We're going to use a lowercase n. That is a lowercase n. And we're going to say that equals the moles. Just the moles. It's not a mole, it's not a molar mass, it's just the moles. Now, what does that mean when we're doing gas law problems? Well, you have a same situation that we had like with degrees Celsius. First thing you got to do is put degrees Celsius in Kelvin, right? Okay, now, first thing you do with moles, you're not going to have moles often. What you will have grams in most problems. Most problems. And the first thing you're going to have to do, just like when we did stoichiometry in Chapter 7, anytime you see grams, the first thing you're going to have to do is you got to get the molar mass. So you will need the molar mass. And we know what the molar mass is. That's grams per mole, right? And you will use this to find the moles. You'll have to do it. And if you get your answer in moles, well, then you'll have to use the molar mass to get it back to grams. So you're almost always going to have grams, and you're going to have to put it in moles. And your answer is going to end up in moles. You're going to have to put it back in grams. Same thing with degrees Celsius versus Kelvin. The problems require you to work it in Kelvin, but the problems are always going to have degrees Celsius. So the first thing you have to do is you got to clean up the units. You got to clean up the units and put them in the right units. So the amount is the number of moles. So to summarize, we have 4 units, just 4 units that we're going to be using for gas law calculations, just 4. And they are P for pressure, it's V for volume, T for temperature, and N, lowercase n, for the amount, which is moles. So there's your 4 units. All gas law problems are going to use just these 4 units. But you may have to take your units that are in the problem, like we mentioned previously. If you need a different pressure unit, you're going to have to convert in between. If you have milliliters and the problem requires liters, you're going to have to put it in liters. If you have degrees Celsius, and you often will, you'll have to put it in Kelvin. And then you have amount, which is the moles. And if you have grams, you're probably going to have your molar mass to put it in moles. So here are the 4 units for gas law calculations.